Welcome back to our IT 7014 series. Today, we're looking at how smart infrastructure systems reduce a building's energy use by up to 40%. To get that kind of reduction, you might assume we need to invent entirely new air conditioners or highly advanced light bulbs. But a building management system, or BMS, does not replace the physical heating or lighting equipment. Instead, it acts as a building's central nervous system. It takes control of these services away from human operators and runs them automatically based on real-time data. Without a BMS, a building is like an unconducted orchestra. You have dozens of mechanical systems all playing their own tune, and often they actively fight against each other. That 40% margin of energy savings is achieved by orchestrating the information flow between the systems that already exist. Historically, a building's mechanical subsystems were installed by completely different contractors. A heating system had no way to communicate with a security system. A BMS brings 6 primary physical subsystems together on one platform: HVAC, lighting, access control, fire and safety, energy metering, and vertical transport like elevators. Left isolated, these systems waste tremendous energy. A heating system might run at maximum capacity trying to warm a room, completely unaware that the security system just opened the ventilation windows on a timed purge. By bringing all of these physical systems onto a single IT dashboard, facilities teams can establish rules to detect and resolve these physical conflicts. The true value of a smart building lies in cross-system behavior. A change in one domain instantly triggers a coordinated response across the facility. So how do thousands of isolated components know exactly what to do without a human pressing any buttons? It all comes down to the control loop. This diagram shows the measure, compare, act cycle. A sensor measures a physical state. The reading goes to the controller, which compares it against the set point. If it misses, the controller commands the actuator to adjust a valve, changing the environment and feeding into the next reading. You have likely seen this logic in your home thermostat. It senses the cold, triggers the heater to reach the target, and turns off. Large-scale building automation relies on this exact self-correcting loop, repeated thousands of times a second across every floor of a skyscraper. Control loops are blind mathematical cycles. They only know how to chase targets, so they require boundaries set by human operators. The first boundary is a set point. This is the specific numerical target the controller tries to reach. It is usually configured as a range, like 22 to 24 degrees, to prevent the equipment from constantly flickering on and off around a single degree. The second boundary is a schedule. This time constraint dictates when the set point actually matters, say 9 to 5 on weekdays, and when the building's temperature is allowed to naturally drift. The final boundary is a rule. This is conditional logic that overrides standard schedules when unusual physical events occur, like shutting off the cooling if someone opens a window. Set points provide the numerical target, schedules establish the daily rhythm, and rules provide the intelligence to break that schedule when reality demands it. Relying on a fixed schedule is a building's biggest energy vulnerability. Occupancy is uneven. Meeting rooms sit empty while open-plan desks are packed. The ultimate efficiency multiplier is occupancy-based control. This strategy shifts the system from anticipating human presence to actively reacting to it. Detecting human presence requires specific sensors, each with blind spots.
PIR motion sensors detect movement, but miss stationary workers. Access card swipes count entry at the door, but only provide broad, floor-level estimates. Carbon dioxide sensors measure human exhalations, which makes them highly accurate for scaling crowds, but they have a delayed response time of several minutes. Then we have device-level Wi-Fi tracking and camera-based human shape counting. While technologically advanced, both face severe privacy and regulatory roadblocks. Because no single sensor is flawless, intelligent infrastructure design relies on layering multiple, overlapping detection methods to paint an accurate picture of human activity. Once the BMS confirms a physical space is empty, it executes 3 specific actions to immediately stop wasting energy. First is set point widening. The system relaxes the temperature boundaries so that heating and cooling equipment can safely power down. Second is demand-controlled ventilation. Instead of running fans continuously, the system scales fresh air intake back based on CO2 readings, which is critical for spaces with highly variable head counts, like lecture halls. Finally, lighting follows presence. The system relies on short timeouts to shut off lights completely after a few minutes of detected stillness. These 3 automated responses, executed micro-regionally across massive structures, are the invisible mechanisms that ultimately generate that 40% energy reduction. Let's transition from theory to empirical data and examine the specific daily load profile of an office building. This chart plots energy load over 24 hours. The orange dashed line represents a fixed schedule, blindly burning 90 kilowatts all day. The green occupancy-based line dynamically follows human arrival and plunges during midday. The gap between them represents the exact carbon and capital saved. The reduction shown in this shaded region is the direct result of using information to replace waste. Let's apply this theory directly to quiz 7 and 8 and identify a few common test traps. Question 1 will ask you to define a control loop. The exam will try to distract you with dense vendor jargon. Cross that out. Look for the simple cycle: measure, compare, act. Ignore the noise and focus strictly on the core definition we established earlier. Question 4 addresses systems architecture. It asks why the supervisory server must remain physically on-site rather than moving to the cloud. Do not be fooled by answers offering speed or cost savings. The ultimate priority for an on-site server is maintaining life safety continuity, like fire alarms when the internet fails. Finally, look closely at question 7, which requires choosing between CO2 and PIR sensors for demand-controlled ventilation in a massive lecture hall. Here is the trap. PIR motion sensors provide binary, yes or no data on presence. That is the wrong kind of data for a space that scales dramatically from 5 people to 200 people. CO2 is the correct answer. It provides proportional data, telling the system exactly how many people are breathing in the space, which accurately dictates how much fresh air is required. True engineering mastery means matching the correct data type to the physical reality of the space you are trying to control. You now understand how every automated decision in a building works, from the sensor reading to the valve opening. In Part 2, we'll explore the 4-layer IT architecture of a smart building, the 3 communication buses, why the supervisory server stays on site, and how buildings connect into smart cities. Stay with me.